Okay. Right, let's get started. Lecture 17. So today we'll discuss alkyne and alkyne reactions. Joy's announcement about the midterm reading is almost over. So currently we have a plan to release the results on this Wednesday, okay, the day after tomorrow. And below you can find the claim period, claim plan this Thursday and Friday. Right? This can be changed, but pretty much sure we can make this happen. So 15s and 16 from 5 to 7 p.m. Okay, and this is the block for the students whose ID ends with odd numbers, right? And students with ID ends with even numbers can visit this time, right? 6 to 7 and 5 to 6 on Thursday and Friday, respectively. 혹시 컴플렉 있는 사람? 지금 TA들이 마지막으로 더블 체크하면서 점수 그리딩은 거의 다 끝났는데 한번 더 확인하고 있고요. 수요일 날까지 저녁까지는 아마 공지가 될 것 같아요. 그래서 수요일 날 공지가 되면 목요일, 금요일 날 바로 클레임 피리어드를 가지려고 합니다. 그래서 5시부터 7시 이 강의실에서 할 계획이고요. 여기가 409호 맞잖아요, 그죠? 그래서 자기 아이디가 끝자리가 홀수다. 그러면 목요일 5시부터 6시 혹은 6시부터 7시 금요일 날 이렇게 오면 되고 내 아이디 끝자리가 짝수다. 그러면 목요일 날 6시부터 7시 혹은 금요일 날 5시부터 6시 이렇게 오면 될 것 같아요. 예년에 클레임 한 거 보면 너무 한꺼번에 몰려들면 학생들 너무 많이 기다리고 TA들도 너무 정신없고 그래서 이렇게 나눈 건데 나는 여기에 다 불가능하다 친구 있으면 이메일을 하세요. 이메일을 저한테 하면 제가 TA들하고 시간을 맞춰서 또 따로 진행할 수 있게 할 테니까. 그래서 클레임 웬만하면 다 모셔서 채점, 내 시험지에 채점 잘 됐나 한번 확인을 해보세요. 클레임도 해보고 저희들이 그리고 저도 채점에 참여했습니다. 제가 저희 분반 한 70%는 제가 채점했어요. 그래서 저도 클레임 때 참여할 수도 있고 또 아니면은 페이퍼에 쓰게 할 거니까 이거는 조금 다시 봐주십시오. 이렇게 글로 남겨놓으면 그걸 TA들이랑 제가 또 확인해서 반영을 할지 안 할지 결정을 하겠습니다. 오케이? 질문 있는 사람? 오케이, 없으면은 저희 진도 나가도록 하겠습니다. Okay. Again, this is the announcement for midterm and claim period. So please participate in this just to check whether your score is right, your grading is okay. All right. And last week, and then maybe the week before we have discussed thus far the reaction of the alkene, and these are stage of the reaction we discussed, right? So this is the exemplary substrate, the cyclohexene, and starting with the HX addition, right? We discussed the addition of water, hydroboration, and oxidation, right? These two, by the way, give you the same product, same alcohol product, but the mechanism was completely different, right? And also the alcohol can be added, right, instead of water, right? In this case, you will get the ether, right, compound. The mechanism is basically identical. Proton addition, and addition of Br minus, halide, water, or alcohol, right, will give you the added product. Right? And also we discussed the addition of the Br2, right, or Cl2, right? So after formation of the cyclic bromonium cation and Br minus attack will give you this bisphenol dibromide or bisphenol dichloride. Right? And for the second step, water, right, can attack the cyclic intermediate, cation intermediate, and this will give you the halohydrin, in this case bromohydrin. And for the recorded lecture, we discussed, we added right, the addition of the peroxy acid, right, which will give you the epoxide, right? So the oxygen is transferred from peroxy acid to the alkene to give you this cycling, right? The epoxide. And this is happening through the concerted reaction mechanism, right? And also we discussed the ozonolysis, the oxidative cleavage of alkene, right? And this will give you, right, diketone products, right? So you can think of like this double bond is cleaved, and each side has a double bond with the oxygen, right? That's the final product. And you have to know the mechanism for ozonolysis as well. And perhaps you reviewed the catalytic hydrogenation reactions in the presence of the heterogeneous catalysts like palladium or platinum, right? On the surface of that, the hydrogenation reaction can take place. So this olefin is simply saturated, right, with the addition of the H2. And the reaction is basically a syn-type addition. And if you know all the details, right, the mechanism of each of the reaction, then you can rationalize the stereochemistry. You don't have to memorize this, right, if you know the mechanism. This is basically a simple rule. Maybe you can double check your rationale or your expectation, right? So this is simple notation, right? If you are running the reaction with the cis, right, substrate, it's a character of the substrate, and if the reaction is syn-type addition, then you'll get cis product or erythro product, right? That's what this notation means. And from this baseline, this reference point, you can change 2 terms, right? But not only 1, right? So from this baseline, right, you can tell, right? Cis substrate with anti-addition will give you thrill or trans product. That's fine because these 2 are changed, right? But this are not. This is not changed. Right? Only 2 terms can change. And if you're running the reaction with the trans substrate and the reaction is the anti-fashion, right, then product will give you, the product will be the erythro or cis-type product. That's fine because you are changing only 2 terms here. Right? What about this one? You changed, right, the type of reaction, the anti-addition. You change only 1, right? You can tell this is not okay. This is not correct. Okay? That's how you can double check. So from the baseline again, right, cis substrate with syn-type addition will give you cis product or erythro product, right? You can change 2 terms. Okay? 그래서 지난주, 지난주까지 해서 저희가 알켄의 어디션 리액션 다뤄봤습니다. 그래서 메커니즘상 유사성이 상당히 많아요. 근데 조금 다른 메커니즘으로 진행되는 경우는 구별해서 이해하시면 되겠습니다. 프로톤 어디션 된 이후에 할라이드 혹은 워터, 알코올 들어가는 메커니즘은 동일하죠. 그렇죠? 그러면 프로덕트로는 각각 알킬, 할라이드, 알코올, 이터가 나오는 반응인 거고, 알코올이 생기는 경우에는 특별히 저희가 hydroboration followed by oxidative reaction, 그렇죠? 그 반응 경우도 공부를 했었고, 그리고 레코드 렉처에서 커버한 부분인데 peroxy acid나 오존이 어디션되는 반응도 좀 메커니즘상 유니크했습니다. hydrogenation, 이거는 surface에서 일어나는 바나듐이나 플라틴 surface에서 일어나는 반응인데 올레핀과 하이드로젠이 이제 surface에서 만나서 syn-type로 일어나는 반응이고, 그렇죠? 그래서 메커니즘만 기억하시면 스티리오케미스트리를 외울 필요 없죠. 그죠? 이거 syn-type이다, n-type이다. 그러면은 인터미디에 생긴 이후에 세컨드 스텝이 어떻게 진행되는지까지 알면 프로덕트가 어떻게 스티리오케미스트리가 나올 건지, 그죠? 외우실 필요가 없고 이해가 되시겠죠? 그러나 이제 내가 빠르게 한번 더블 체크를 해보고 싶다 그러면 이 룰을 한번 적용해 보셔도 나쁘지 않다. Okay, so that's what we covered for the alkene, and we're moving on to the alkyne and its reaction. Right? There's a commonality between alkene and alkyne, so it's not a complete new thing, probably. These are the exemplary alkyne molecules, which are naturally occurring, the above line, right? These are the natural compound, the above, right? And you can identify the alkyne functionality here and there, right? And this is the diene, meaning you have alkene and alkyne in series, right, in conjugated form. Right? This is a class of the anti-cancer drug and very important compound. And there's synthetic alkyne too. So the bottom ones are what we make, right? What we can make, right? It's a synthetic one. The alkyne is here and there. So very, very important compound as well. So alkyne is very, products is very important. That's why we need to study, right? The structure, nomenclature, and also its reaction. And since this is the first time we study alkyne, you need to know how to call it out, right? So nomenclature of the alkyne and general formula is the following, right? The acyclic means the linear one versus cyclic one, and perhaps you can tell by degree of saturation. We study the normal alkyne, a molecule containing one triple bond, its DU has to be 2. Right? But if you have one cyclic structure top of that, then DU will become 3. Right? So starting from the saturated general formula, Bn H2n plus 2, right? You can rationalize why the acyclic compound, the alkyne compound, has this general formula. Right? This will give you a du over 2, right? And this 2n minus 4 will give you a du over 3. Right? So 2 come from alkyne, 1 from cyclic structure. Okay? So that is a general formula, but if you have one more, right, alkyne, then you can calculate the du accordingly. And this is a exemplary alkyne, its name, right? And there's two different alkyne actually. So if you take a look at the second one versus third one, right? You have an alkyne which ends, right? The one of the end, right? The hydrogen. Then we call this as terminal alkyne. But if both sides of the alkyl group doesn't have any, right, hydrogen on either side, then we call out as an internal alkyne. So you need to know terminal versus internal alkyne. Right? That's naming first, very straightforward. Right? And the basic rule is you have to identify the number of the carbon in the chain, right, containing alkyne, and the chain is then numbered in a direction that gives the Y and E in suffix, okay, the lowest possible number. So every compound here is called out as an in, right? Butene, pentene, and hexene, okay? And you have to identify the longest possible chain that contains, right, this triple bond. And you can, of course, put the number, right, for the carbon starting with the alkyne, the triple bonds, right? And you can take you can practice, but basically the same will apply as you already know, right? The alkene, right? The nomenclature system basically works very similarly to the alkyne. So perhaps you can compare left and you can try to make a name, right, for left and right, right? So for this one, right, you can first identify the longest possible chain containing this functional group, right, the alkyne, right, which has to be this, right, containing 8 carbons, right? That's why this compound is, at the end of the day, has to be called out as an octene, right, and with Y and E, but with 8 carbon, that's why you have to call out as an octene, right? But you have a choice, starting carbon from left-hand side or from the right-hand side, right? And you can put the number from 1 to 8, right, from left to right, or 1 to 8 from right to left. Right? But you have a choice from left to right in order to make this carbon as the lowest possible numbers. These carbon contain, right, the halo group, chloro and bromine group. Right? That's why you need to start from left. Okay? And then you can identify 2 chloro, 3 bromo. Let's start with B, right? Following the alphabetical order. So 3 bromo, 2 chloro, and you have to notify the location where the triple bond starts, right? That's number 4 carbon. So 4 OT. Okay? And you can do the same thing for the right one. Okay? And as we discussed for the alkene, right, there might be a compound that contain, right, triple bonds in 2 locations. In this case, you can call out the diene, right? And you can identify the position of the carbon, the starting carbon, which is 1 and 4. Right? That's why this is called 1-fo diene at the end of the day. And you have 1, 2, 3, 4, 5, 6 methyl. Right? That's why you have to call out this 6 methyl hepta 1,4-diene. The location of 1,4, right, can change, right? Same rule applied for alkene, right? So you can call out the 6 methyl 1,4-heptadiene as well. Okay? And the reason why this carbon is number 1, because that's how you can make, right, the carbon containing alkyne as the lowest possible number. Right? And you can encounter this case too. The molecule contain both, right, a double bond and triple bond. Right? In this case, you have double bond here and a triple bond there, right? And then, of course, you can identify the longest possible chain, right, which is this, in this case, very straightforward and obvious, has 7 carbon. So this is a heptane based, right? But you have to choose the number from right to left to make, right? The carbon contains double bond or triple bonds. In this case, triple bond is the lowest possible number, right? Then you can put number 1 here and number 5 there, right? Then you can call out then 5 heptene 1 ene. Okay. What about the next one, right? Again, you can identify the longest possible chain, right? But in this case, right, you have to choose from left to right in order to make this carbon, right? Number 1, right? The carbon contains double bond or triple bond as low as possible. Right? In this case, the alkene, right, double bond containing carbons should start with 1 here. So you can identify then number 1 carbon for double bond and number 5 for the triple bond. The carbon starting with the triple bond, right, from left to right. And then you can pull out this the ene first, followed by ene. So 1 heptene and 5 ene. That's the name of this compound. And what about the bottom case, right? So you have to identify first the longest possible chain that contain both functionalities, functional group. Okay? So in this case, you cannot, right, make the main chain like this, then you're missing this alkene. You cannot choose this chain either because you're missing this functionalities as well. Right? So you have to choose in this case these as a main chain. Even though this is not the longest possible chain you can identify. Right? You have to choose the main chain that contain both important functionalities. You cannot just miss any functionalities, right? Functional group here. Okay? And then you can call out from left to right, right? To make the starting carbon, the starting double bond, right? Carbon is number 1, right? And then this carbon is going to be number 4. Right? So this is going to be eventually 1 hexene 5 ene, right? but you have the butyl group, right, at 3 position. That's why this is 3 butyl, 1 hexane, 4 ene. Right? And this is what I already explained. The longest continuous chain is 8 carbon in this case, but 8 carbon chain does not contain both functional groups. Therefore, the compound is named as a hexane ene, right? Because this is the only possibility that contain both functional groups, right? The longest continuous chain contain both functional groups, right? Which have 6 carbons. Okay. This is a special case, right? But you may encounter, right, when double bond and triple bonds are tied. Right? In this case, double bond wins. Right? So take an example here, right? You have the longest possible chain first, of course, 6 carbon. That's why this is a hexane base, right? But in this case, you have to choose for the numbering from left to right or right to left, right? You choose left to right, then this carbon is going to be number 2. But if you choose from right to left, then this carbon is going to be number 2. Right? These are tied. Right? The starting number is the same from left to right and right to left. But in this case, you have to choose from left to right because alkene has a higher priority. Okay? So you can make number 1 carbon from left, 2, 3, 4. So starting carbon for alkene is number 2. Starting carbon for alkyne is number 4. Okay? The next one, the alkene first, again, 2 hexene, 4 ene. Okay? That's a correct number. You can apply the same rule for the right hand side. This is in the case when the location of double bond and triple bonds are tied. So when the same number is obtained for both the double bonds and triple bonds, then double bond gets a lower number. Okay? And this is the sort of like a priorities table, priorities of the functional groups of peaks. Okay? And this is what we just discussed. Okay? When they do have pretty equal priority, but when they tie, then alkene means double bond is given priority or triple bond only when there is a tie. And compared to double bond or triple bond, amine has a higher priority, right? And compared to amine, alcohol has a higher priorities too. And in OChem2, you will study a lot about the carbonyl. But for your record, your information, now you can like carbonyl has the highest priorities in this stage. Right? So when alcohol and amine has to compete, they have to compete, then you have to choose alcohol. Right? Followed by amine, double bond, and triple bond. So you can maybe practice, right, following the rule we just discussed. The alcohol and amine have a higher priorities. So in this case, right, you take a look at, then you have to choose this carbon has to be number 1. Right? Not this carbon. Right? And you can put the number, right, 2, 3. Right? Then you can identify the carbon having alcohol is number 1. That's why this is 1O. Right? And you have number 2 carbon starting by the double bond. That's why this is the 2 propene 1O. Okay? You can apply the rule basically here and there, right? Across all these examples and tests here the same. Right? Again, you have to apply, right, the priorities. Alcohol means amine, and amine means double bond and triple bonds. 그래서 이제 노멘클레처 관련해서 꽤 많이 공부를 했어요 저희가, 그죠? 알로그룹부터 있는 경우 처음에 알켄 할라이드도 명명해서 알켄으로부터 시작해서, 그죠? 근데 이제 functional groups of fix가 붙는 경우가 있고 substituent로 분류되는 경우가 있었어요. 그래서 그거를 구별하실 줄 알아야 되는 거죠. 구별을 하실 줄 알아야겠죠. 할로그룹은 예를 들면 저희가 functional groups of fix 처리를 하지 않았어요. 그렇죠? 할로, 오시기 이렇게 뒤에 붙여서 substituent 처리를 했었고, 알코올이나 아민이나 더블 번드나 트리플 번드를 가지고 있는 이제 functional group은 저희가 functional group 처리를 했어요. 그래서 이름 자체 끝자리를 이제 저희가 무슨 알코올, 무슨 아민, 무슨 N, 무슨 in 이렇게 명명을 하게 되는 거예요. substituent는 앞에 붙는 거예요. 그렇죠? plural 뭐 한노, 브로모, 메틸, 그렇죠? 등등의 substituent 처리가 되는 거예요. 그거를 노멘클처 공부하실 때는 구별만 하실 줄 알고 기본 룰들 거의 공통적으로 적용됩니다. 그래서 공통 적용해서 연습하시면 되겠습니다. Alright, that was the nomenclature, right? So you have to know again the priorities, right? Alcohol, amine, triple bond, right? Double bond, and also you need to distinguish whether you're dealing with the function group versus substituent. Right? For instance, like the halo group is a substituent that are functional groups. Okay. Right. What about the structure, right? And as we discussed in chapter 2, yes, right? Alkyne is a triple bond, and this carbon, right? The constituent carbon for triple bond, they have two arms, right? So you can tell the central carbon has to be sp hybridized, right? And there's a remnant 2 p orbitals which can formulate the pi bond in perpendicular fashion. Right? So this is a picture indicating the pi bonding system in alkyne, right? sp hybridized orbital formulate the sigma bonds, right? So there's a sp-sp overlap for the sigma bond, right? So there's a sigma bond in between 2 carbon sp hybridized orbitals, and there are 2 remnant p orbitals for each carbon, right? Sitting perpendicular to each other, right? And then, right, the parallel component will formulate pi bond. So blue will formulate 1 pi bond, and purple will formulate the other one. Okay? So in total, you'll have 1 sigma and 2 pi bonds. That's how you are getting the triple bonds. Okay? And of course, right, alkyne is a linear. So sp hybridized, there are only 2 arms, right? So it's geometric, linear structure. What about physical properties? This is a sort of like series of the bonding points, right? On left hand side, arcane, and alkyne, right? As a function of the carbon chain, right? Number of carbon chain. If you compare arcane versus alkene, your bonding point trends are very similar. There's a small difference, but largely very similar. If you compare, right, alkene versus alkyne, alkyne, its bonding point is higher, right? Around 20 degrees, right, per each chain. Right? Compare, for instance, propene versus propene, right? There's a 20 degree difference, right? What about pentene? Pentene case only 10 degree difference though, but if you compare, right, what about cis-2-butene versus 2-butene, right? There's about 20 degree difference, right? The reason for alkyne having higher boiling point is that alkynes, generally speaking, have a stronger van der Waals interaction, right? Alkynes are more linear, and alkenes and triple bond is essentially more polarizable, right? There's more electron density within the localized, right, area. It's more polar in general, so intermolecular interaction will get higher, right? In alkyne, that's why the bonding points are, generally speaking, higher. Okay, what about reaction? And that's what we care about, right? In this chapter, an alkyne like alkene, you can undergo electrophilic addition reaction, right? So alkyne and triple bond, there's an electron, right? It's an electron-rich area, the localized area. So this can attack, right, the electrophile like proton, right? In this case. So here, the electron-rich component in triple bond serving as a nucleophile and participate in electrophilic addition reaction. Okay, so as a result, right, 1 pi bond is broken, right, and 2 sigma bond is formed between this carbon and fluoro group and this carbon and hydrogen group. And we'll see later, the second step can also take place with the second addition, basically, to give you the geminal dichloride in this case, not this one. Okay? So we'll see that in a few slides later. So you can compare the first step, right? First step is still the addition of the electrophile, but the alkene versus alkyne, right? There's a similarities and also the difference, right? So again, from the left-hand side, this is what we studied last week. Alkene can attack the proton, right? Protonic site in HX, right? HCl in this case to generate the carbocation, right? This is alkyl carbocation. And you know the second step, right? Chloride attack this carbocationic center will give you, right, the added product. But for the alkyne case, you're starting with the triple bond, right? And this is again, right, electron-rich area, so this can attack easily, right? This electrophilic site, electrophilic atomic site, in this case proton, right? After, right, the first step, instead of like alkyl cation, there's double bond exists, right? Because you start with the triple bond. And essentially you're generating this binylic cation. This is what we call binylic cation. Okay? You have the double bond, right? And the carbon that has the double bond directly, and positive charge on that carbon. If that is the case, then we call the binylic cation. So that's the difference. The general scheme is quite similar, right? Only difference is you have the double bond after first addition. And this is a relative carbocation stabilities, right? And you already know tertiary carbocation is more stable than secondary carbocation and primary alkyl cation and methyl carbocation. This is what we already know, right? And we are basically inserting here the relative stability series of the binylic cation. Okay? So compared to the secondary alkyl, right, carbocation, right, secondary binylic cation is less stable, but this secondary binylic cation is more stable, or actually quite comparable, showing comparable stability with the primary alkyl carbocation. Right? What about primary binylic cation? It's less stable than primary alkyl carbocation, but this is more stable than zeroth order the methyl cation. Okay, and this methyl cation, right, is more stable than binylic cation. So for the same order, right, generally speaking, alkyl carbocation is more stable than binylic cation. Right? So why that is the case? Binylic cation is less stable than similarly substituted alkyl cation because binylic cation has a positive charge on the sp carbon, right? And as we studied in chapter 2 or 3, right? Sp hybridized carbon has a higher electronegativity than sp2 or sp3 hybridized carbon. You have higher, right, S character. That means your element has a higher electronegativities, but you have to put plus charge on that, right? Which is not happy situation. sp carbon is more electronegative than sp2 carbon and alkyl cation, so less preferable pure positive charge. That's why, right, the binylic cation is less stable than similarly substituted alkyl cation. 그래서 carbocation stability 시리즈는 이제 유기화학 공부하시는 데 있어서 계속 베이스라인이 될 것이기 때문에 원리를 이해하시는 게 중요하죠, 그렇죠? 그래서 저희가 알켄의 어디션 공부할 때까지는 하더라도 알킬 카보캐라인의 안정성 이야기만 했어요. 원래는 하이퍼 컨주게이션 효과 공부하셨던 거 기억나실 겁니다. Basically, 카보캐라인 주변의 알킬 그룹이 일종의 도네이팅 그룹으로 작용해서 포지티브 차지를 좀 안정을 시킨다, 이렇게 생각하시면 되겠죠. 좀 더 리거러스한 해서는 하이퍼 컨주게이션 효과였다. 근데 이제 알카인으로 넘어와서는 first step, 프로톤이 들어가고 나면 이제 더 이상 알킬 캐라인 형태가 아니라 바이너리 캐라인 형태로 인터미디에이트이 주어지니 이제 바이너리 캐라인의 안정성도 제가 공부를 하고 있는 것이고, 바이너리 캐라인의 안정성을 이제 일전에 배웠던 알킬 카보 캐라인을 이제 안에 집어넣어 보고 있는 거고요. 제너럴 트렌드는 같은 오더, 같은 치환된 정도의 알킬 카보캐라이온 대비 바이너리 카보캐라이온이 덜 안정. 그 이유는 플러스 차지가 일렉트로네거티브 캐릭터가 높은 sp 하이브리다이즈되어 있는 카본에 플러스 차지가 들어가야 되기 때문에 해피하지 않은 상황입니다. 그렇죠? 그렇기 때문에 안정성이 좀 떨어질 것이다. 이렇게 이해하시면 되겠습니다. Okay? This is a little bit trickier one. This is the structure that people propose, right? Or the addition function of the arcane. And people argue that the pi complex looks like this will be formed, right? Instead of the binylic carbocation, right? Binylic cation, especially primary binylic cation, is too unstable. It's less stable than even primary arcane, right? It's hard to form. Right? So it's been proposed that intermediate like this, right? Pi complex is proposed instead. You see this, right? Pi complex. There's a partial, right? Bond character between this carbon and carbon. This is not essentially triple bond. This bond, one of the bond is essentially broken, right? Instead, they made partial bonding character between hydrogen, right? And positive charge is essentially residing on this, right, hydrogen instead of the binylic site, binylic carbon site. Right? Usually, positive charge is sitting relatively away from the carbon site, which is good for the stability of the system. Okay? So it is more stable than the binylic cation that we discussed in this series, right? But it is not as stable as an arcane still. But it is better than just binylic cation. That's why people propose this structure. And there is some evidence right after formation of this postulated structure. If you can imagine, right, if this is formed as intermediate, then the second step, right, nucleophile attack, the chloride, for instance, will attack one of the carbon, right, and then you will get the anti-product, right. That's what people argue. Formation of G isomer in this case, right, hydrogens here and there, chloride there. Evidence for the formation of the pi complex. This is just a word product that we have seen. Right? So from this evidence, we argue that instead of like formation of the binylic cation, the pi complex will be formed as a relatively stable medium. 그래서 binylic cation에 대한 이야기를 하고 있는데 이제 터미널 알카인의 어디션이 일어납니다. 반응이 일단 진행됩니다. 터미널 알카인에 HCl 어디션하는 반응이 진행돼요. 근데 HCl이 들어가는 경우를 생각해 보면 앞에서 다뤘던 메커니즘에 의하면 결국 primary binylic cation이 생겨야 되는데 primary binylic cation은 저희가 앞에서 공부한 시리즈에 의하면 primary alkyl cation보다도 안정하지 않아요. 그렇죠? primary cation, alkyl cation만 해도 별로 안정하지 못해서 그 패스웨이가 진행되기 힘든데 그보다 더 안정하지 않은 인터미디에이트에서 어떻게 반응이 진행될 수 있냐 사람들이 argu를 한 거고 그것을 해결하기 위해서 제안한 것이 이런 인터미디에이트에 생기지 않느냐 파이 컴플렉스와 같은 이 파이 컴플렉스가 생기고 반응이 진행되면 그래도 프라이머리 바이너리 캐라인을 생기면서 진행된 경로보다는 더 진행이 잘 되지 않을까 그렇게 생각을 한 겁니다. 그것의 에비던스로 이제 인터미디에이트이 생기면서 반응이 진행되기 때문에 엔타이 어디션 때 G 아이소모만 생기는 거 아니냐 이게 생기는 게 에비던스라고 주장을 한 겁니다. 만약에 파이 컴플렉스가 생기지 않고 바이너리 캐라인이 생겨서 진행된다고 하면 G폼, E폼 섞여서 생겨야 되지 않겠나 근데 G폼만 생기는 걸 보니 파이 컴플렉스 같은 인터미디에이트 생긴 이후에 엔타이 어디션이 일어난 것 같다. 여기까지 사람들이 레슨을 제공한 겁니다. Alright, so that was the claim that people made for the formation of this pi complex instead of the binylic cation, which is again relatively stable, more stable than the binylic cation, but still relatively unstable than primary alkyl cation. It should be in between, right? But still better, again, better than primary binylic cation. And after the first addition, right? So this is the halo substituted product, right? After first addition, right? addition of HCl, right? And then the second addition can take place, right? Still, right? You have the double bonds, right? We'll discuss this later, but because of this chloro group, this alkene has a lower reactivities than just normal alkene. But still, right, the halo substitute alkene has some reactivities towards the electrophilic addition. So second addition can take place, right? So you can think of, right, the normal HCl addition reaction with the alkene, but in this case, right, you are generating this geminal dihalide, meaning two chloro groups sitting on the same carbon. We define the bisphenol dichloride or dibromide, right? Or the addition reaction of the Br2 or Cl2 in the chapter of the alkene. The bisphenol meaning, right, you have two different carbons that has, right, the functional group, right, independently. The geminal means, right, same carbon, right, has two substituents, two functional groups. Right? In this case, chloro substituents. Right? In this case, we call it geminal. Okay? And you have the carbon sitting next to it, and each has functional group or substituent. We call this the bisphenol. Right? So bisphenol versus geminal. That's a terminology for distinguishing the location of two functional groups. Right? And same carbon or geminal versus two different carbons sitting next to it, the bisphenol. Okay? So for the addition reaction of the alkyne, for the second addition of the HCl, you're generating the geminal dihalide. We'll discuss what that should be, why this should be the case. Right? Addition to a terminal alkyne, if you think about from the beginning, with the first addition, right? First addition will give you, if you're running the reaction with butene, you will generate this product. This is reduced selected because you're getting only one product, right? Proton added to the terminal position, terminal carbon, right? Then chloro group added to the carbon next to it. Right? This is the only product you're getting, right? And that's why this is a reduced selective reaction, and in particular running the reaction with the terminal alkyne in this case, right? So why that should be the case? This is the mechanism again for the electrophilic addition of the terminal alkyne, and as we discussed, after, right, proton addition, instead of like the primary binary cation, you would generate probably the pi complex looks like this, right? And then nucleophile attack, in this case chloro group attack from more substituted carbon, as we discussed, right? Basically same argument applied here for the alkene. And then, right, you are generating this final product after first addition, right? So first equivalent of HCl will be added and give you this product. And I guess we have a transition state argument, right? Why chloro group attack more substituted carbon in this case, right? And this is the transient state. Chloro group, the nucleophile attack more substituted carbon versus less substituted carbon, or in other words, chloro group attack the internal carbon versus the chloro group attack the terminal carbon, right? Or you can identify this as a secondary carbon, and this one is the primary carbon, right? In this case, right, this is a transient state, right? And this one, right, this is more stable, right? Because you have, right, the delta plus with more substituted secondary carbon. You take a look at the transient state and charge analysis, right? And carbon that accommodate the chloro group as a partial positive charge, right? Then it's probably better, right? If you have more R groups around. Right? So that's the simple rationale why the chloro group for the second step attack more substituted carbon. Okay? Second step, second electrophilic addition reaction is also reduced selected. So after formation of this, right? For the second equivalent addition, HCl is also selected, right? To give you the geminal dichloride product. So proton added there and chloro group added there in all cases, in most cases. Right? That's why this is reduced selective. Right? And again, you can basically make an argument, right? So this is a case when proton added to the more substituted carbon, and right hand side is the case when proton added to the less substituted carbon, and there's a rationale why right hand side is more preferable, more stable. And the left hand side, right, you have the primary hydrocation, which is not happy in the first place, and you have a chloro group which can withdraw the electron density from the inductive effect, right, which is that. The right hand side though, right, you have the secondary carbon cation, right, positive charge and more substituted carbon. On top of that, still you have a inductive withdrawing effect though, but there is a donation effect from the chloro group as well. Chlorine can share a pair of electrons, right? And as a result, you can draw the gradual structure. You can basically delocalize the positive charge, right? You can basically extract the positive charge on carbon to the other place, right? So you can stabilize the overall system, right? That's why, right, the right hand side is more preferable, right? And why proton added to the terminal position, right? And then chloro attack, right, more substituted. And that's why we are getting this general dichloride. And this is the relative reactions, alkene versus alkyne versus halosubstituted alkene. And as I mentioned earlier, right, briefly, the halosubstituted alkene is the lowest reactivity since it's not reactive than normal alkene and alkyne, right? Because the halo group, right, generally speaking, withdraw electron density. So the alkene and the electron reach area will lose the electron densities, right? So its nucleophilicity will decrease accordingly. So generally speaking, again, halosubstituted alkene is less reactive than alkyne. So if you can control, right, the reaction well, then you can stop. You can stop the reaction of the alkyne after the addition of one equivalent, because this one is less reactive than alkyne, the initial substrate. Okay? So if you can control maybe stoichiometry of the reaction, or you can control the reaction temperature or reaction conditions, right? And then essentially stop the reaction after first addition to get the halosubstituted alkene. So, well, halosubstituted 프로덕트가 이제 알카인으로 시작되면 first addition 되고 나면 프로덕트로 나오는데 이제 second addition이 또 일어난다라는 것을 저희가 앞에서 계속 공부한 거예요, 그죠? second addition도 reduce selective하다. 프로톤은 less substituted 카본에 붙고 할로 그룹이 more substituted 카본으로 붙으니 이제 germinal dichloride가 생기는 이유가 됩니다. rational은 저희가 여기서 다뤘습니다. 세컨드 스텝에 있어서 이제 프로톤이 한번 붙고 난 이후에 생각을 해보면 왼쪽 오른쪽을 비교하면 되겠죠. 왼쪽인 경우에는 positive charge가 less substituted 카본에 일단 있으니까 일단 회피하지 않는 거고, 거기에 더해서 클로로 그룹이 주변에 있는데 클로로 그룹이 이제 일렉트론 withdrawing 그룹을 작용하죠. 전기 운송 때문에. 그래서 시그마 번드를 통해서 전자를 당기는 효과를 저희가 인덕티브 효과라고 공부했습니다. 그래서 두 자리 정도 떨어져 있지만 여전히 인덕티브 효과가 가능한. 오른쪽인 경우를 이제 왼쪽인 경우를 베이스라인으로 해서 비교를 해보면 퍼지티브 차지가 애초에 더 substituted 카본에 앉아있죠. 일단 회피하죠. 근데 클로로 그룹은 이제 바로 옆에 붙어있어. 바로 붙어있어. 여전히 인덕티브 withdrawing 효과는 있겠구나라고 생각할 수 있지만 클로로 그룹은 또 론 페어가 옆에 있어서 레조넌스를 만들 수가 있어요. 그래서 레조넌스적으로 봤을 땐 또 도네이팅 효과가 있는 substituent라고 저희가 분류를 합니다. 그래서 론 페어 하나가 이제 카본으로 넘어가면 오른쪽에 있는 레조넌스 스트럭처가 하나 나오겠죠. 그래서 레조넌스 도네이팅 효과는 또 동시에 있어요. 이 레조넌스 도네이팅 효과는 왼쪽에서 일어날 수가 없어요. 두 자리가 떨어져 있기 때문에. 오른쪽에서는 바로 전달이 가능하기 때문에 레조넌스 도네이팅 효과도 있다. 그래서 인덕티브 효과는 조금 더 전자를 당기는 쪽으로 작용할 수 있으나 이 레조넌스 도네이팅 효과가 있기 때문에 쌤쌤 친다고 치고, 그러면 애초에 positive charge가 or substituted 카본에 있으니 더 preferable 하다. 종합적으로 따져보면 그렇죠. 그것이 germinal dichloride의 선택성에 대한 이유가 된 것이고, 일반적으로 봤을 때 hallow substituted alkane이 그러면 일반 알킨, 알카인과 리액티비티가 떨어져요. 반대로 우리 아까 이야기한 withdrawing 효과 때문에 파이 전자 일렉트론 덴시티를 조금 줄이는 역할을 하겠죠. 일렉트론 위치해야 일렉트릭 플래그 어디션 반응이 애초에 자리를 내. 그건 기본 대전제예요, 그죠? 근데 할로 그룹이 전자를 땡기고 있으니 일렉트론 덴시티가 줄어들 거 아니에요. 그러면 애초에 반응성이 떨어지게 됩니다. 그렇죠? 그러면 알카인 대비 리액티비티가 떨어지니까 프로덕트로 나오는 애가 반응에 참여할 수 있으나 저희가 반응을 이제 원 equivalent addition 이후에 스탑할 수도 있지 않겠냐. 그러면은 반응을 끝까지 진행된 geminal dichloride 얻지 말고 한번 어디션 된 그죠? binary chloride에서도 멈출 수 있겠다. 이런 생각을 할 수가 있겠죠. And this is a free energy diagram, right? Comparing. This is a very general scheme, so there might be an exception, but this is pretty much generalized scheme and general argument. Alkynes are less stable. Right? So alkynes are sitting slightly above than alkene, okay? And also less reactive than alkene as well. So if you compare the kinetic barrier, right, after first proton fusion, right, alkyne will give you a pi complex as we discussed, right? But the alkene will give you the RQ cation. If you compare the stability of this too, right? The RQ cation is more stable, generally speaking, right, as we discussed, than pi complex. And applying the Hammond postulate, you can then argue the energetics of the transition state for the alkyne's addition is higher, right, than the transition state for the addition reaction of the alkene. And there must exist a delta, okay? You can see that. And there's a difference, right, the energy difference between alkyne and alkene in the first place, right? And the difference in stability of the transition state, right? This delta is generally speaking larger than the initial difference, right? Between alkyne and alkene, right? So the energy difference between two transition states is a lot bigger than the initial energy difference, and that gives rise to larger delta G double dagger for alkyne case versus delta G double dagger for alkene case. Right? That's why, right, alkyne are generally speaking less reactive than alkene, and this is what. That means difference in stability of the transition state is greater than difference in stability of the reactants that give rise to larger delta G double dagger in alkyne case. Right? That's why alkyne is less reactive than alkene. 더 나가고 싶은 진도가 있었는데 조금 있고. 그래서 여기 간단하게만 다시 설명해 주면. 일반적으로 알카인과 알켄의 리액티비티를 비교할 때 알카인이 조금 리액티비티가 떨어진다는 이야기를 조금 이해가 안 될 수도 있어요. 처음 생각하면 알카인이 더 좀 위치하지 않나, 그래서 반응성이 더 좋아야 되지 않나 이런 생각을 할 수도 있는데, 이제 일반적으로 알카인의 반응성이 항상 그런 건 아니에요. 서브스트레이트에 붙어있는 거에 따라서 차이가 있을 수 있어요. 이건 아주 제너럴한 아르구멘트인데, 알카인이 보통 less reactive하다고 이야기를 합니다. 알켄보다. 그 이유가 무엇이냐? 알카인이 알켄보다 이제 사실 에너지 차이가 또 서브스트레이트마다 좀 달라요. 그래서 항상 일반화할 수는 없으나 차이가 거의 없다고 보고, 알카인이 조금 더 불안정하다라고 보면 이제 더 polarizability가 있고 스트레인이 존재하고 그렇기 때문에 조금 더 알켄보다 unstable하다라고 치고, 그러면 이제 결국 반응성이라고 하는 것은 속도라는 것은 리션 반응에 대해서 이제 kinetic barrier를 저희가 생각을 해야 되는데, barrier를 생각하는 데 있어서 저희가 intermediate의 에너지가 중요하다라는 것은 해먼 postulate에서 공부하면서 익혔어요, 그죠? 해먼 postulate에 의해서 첫 번째 스텝 intermediate 에너지는 third process이고, TS가 intermediate 구조와 가까운 것이고, energetics도 intermediate의 에너지를 저희가 관찰을 하면 어느 정도 유출할 수 있다. 그러니까 해먼 postulate이죠. 에너지적으로도 가까운 구조적으로도 가깝다. 이런 이야기를 했었고요. 파이 컴플렉스가 RQ 캐나인보다 더 불안정하다라는 것은 앞에서 디스커션을 했습니다. 그렇죠? 그러면 파이 컴플렉스가 RQ 캐나인보다는 위에 있을 거고, 인터미디에이트 에너지 관점에서. 그러면 해먼 포스츄레이션을 저희가 적용하면 트랜지션 스테이트도 파이 컴플렉스를 형성시키는 패스웨이가 더 높게 유지가 되겠죠. 그렇죠? 알킬 캐라이온을 거쳐가는 패스웨이입니다. 그래서 여기만큼의 델타인 TS가 존재할 수 있는 것은 해먼 포스트레이트 적용하면 받아들이실 수 있을 것인데 이제 알카인이 알켄보다 반응성이 떨어진다라는 이제 설명을 하기 위해서는 요만큼의 차이가 그죠? 요 초기 시작되는 요 에너지 디퍼런스보다 커야 되겠죠. 그래야 델타 G 더블 키네틱 베리어가 알카인의 케이스 초록색 화살표로 표시되어 있는 경우가 더 크게 나타난다. 그게 논리입니다. 그렇죠? 결국에는 TS가 더 높다. TS 에너지가 더 높은 이유는 인터미디엇 에너지가 하이 컴플렉스 알키케라보다 더 불안정하기 때문에 에너지적으로 높은 위치이기 때문에 이니셜 포인트는 알카인 뭐 비슷하지만 알카인이 조금 더 높다고 치더라도 TS에서 에너지 차이가 훨씬 크다. Okay. Alright, so that was the rationale, the general reactivity trends versus alkyne versus alkene. And we discussed in the previous slide major selectivity of determining alkyne. But you can think of like reaction of the internal alkyne. In this case, you have the asymmetric case, right? This carbon has ethyl group, this carbon has methyl group. This is unsymmetrical internal alkyne, right? And then you can imagine, right, that the excess amount of HBr is introduced to this reaction. Then second reaction will take place, but there's a choice, right, for the formation of the geminal dibromide in this case, occurring at this carbon or this carbon. So those two will get will be obtainable as a mixture, as a product. So the second, right, the addition of the HBr. What about the symmetrical case, right? Obviously, you'll get only one product, right? So regardless of right, the general addition take place, this carbon or this carbon, you're getting the same one because it's a symmetrical case, right? Addition of Cl2 and Br2, right? So if you think about the mechanism for addition of Cl2 and Br2 for the alkene, you can easily rationalize how this case, how this final product will get obtained, right? After first addition, right? You can imagine same, right? Cycling intermediate is formed, right? After first attack and then chloride attack, the anti-fashion, right? Where this, right? You will generate this anti-added product, and then the same reaction, right? With in this case, alkene can take place. The cyclic intermediate form and chloride attack here or there, right? Will give you the final product. And same thing can take place for Br2 addition as well. After first addition and second addition, you will get this tetra substituted products, right? So the mechanism of the reaction is exactly the same as the mechanism of addition of Cl2 for Br2 and alkene. 네, 시간이 돼서 이제 알카인의 반응성 차이, 알켄하고 굉장히 유사성이 있습니다. 근데 차이가 조금 있고, 알켄의 메커니즘을 근데 정확히 알고 계시면 알카인 공부하는데 엄청 수월할 거예요. 그래서 내가 알켄 아직 좀 익숙하지 않다. 그럼 빨리 리뷰를 하셔야 됩니다. 알카인이 누적되면 정신 못 차리세요. 반응이 엄청 많이 나와요. 계속해서. 그래서 알켄서부터 다시 리뷰하시고 알카인 다음 시간에 이어서 하도록 하겠습니다.